Today I want to talk about my latest publication with Lennart about quantum walks. First I want to tell you why we study quantum random walks. Then I will tell you about the classification and finally give you the comparison to classical random walks, where the classical random walks start right away. So generally classical random walks, we have some walker, let's say, that is a point and that moves through space randomly. So at some time step we choose a random direction. Then the walker walks and picks another random direction and so on, and the resulting motion can describe Brownian motion, and it's also visible in diffusion processes. One way to model that is using a Markov chain. That is, we have some line and we look at the direction. So we have one state that is we go left, one state is we go right, and the Markov chain just tells us probabilities if we were going left or right. Would we go left again, or would we go and turn right? So how does this go to the quantum world? So instead of being purely probabilistic, we have now superposition of different states. So the walker might be on different positions at the same time. And we model that based on the square summable sequences, tensor product with C2, where C2 is just the same as before, either going up in the line right or going down on the right. So this is the basis of the walker space or the coin space. And what we do in each step, we first apply a coin flip operator, that is this unitary operator, which can be parameterized using three angles. And afterwards we do a conditional shift. So conditioned if we have the up state, we go up the line, so we move from, let's say, from 1 to 2 or from -1 to 0. And if we were in the down state, we would go exactly in the opposite direction. The first difference that we see is if we plot the variance, or the variance square of the variance, as a function of time or the number of steps, then we get a quadratic scaling for the variance in the quantum random walk. And if we have a classically correlated walk, then we have a linear scaling, except for, of course, the edge cases. And here we use, instead of the unitary, we use the stochastic matrix M instead of the coin. So now comes our result, the classification of quantum random walks. So the first part is the symmetric walks. So the first result is that for every initial state there exists some unitary, a coin operator, such that the walk is symmetric. And to answer the question how many symmetric quantum random walks are there. We know that some coin setups are equivalent, and we actually only have to consider this coin. So for every coin there exists some equivalent coin, which is just this Y rotation. And the theta is between 0 and pi over 2. As edge cases, we have the Hadamard walk, that is at theta equals pi over 2, and for theta equals 0 we get the identity, which is just the trivial walk that just goes out on the outside. And for all of those coins we use the same initial state, which is just the up state. Okay, so if we consider now not only symmetric walks but also general walks, we see that there is some dependence on the initial state, and we can parameterize all walks by using this parameterization for the initial state and this parameter range. So we get a quarter of the Bloch sphere. For this you have to be cautious because this parameterization is not yet unique, so you can have different parameters inside this range, but still the walk might be the same. We can make this unique by just classifying the limiting distributions. So the limiting distributions are calculated in a work by Norio Kono, and those are the limiting distributions. And we find that if we again take the coin parameter in our range and exclude the trivial walk and the Hadamard walk, then we get all possible limiting distributions by choosing either those ranges for the azimuthal angle and 0 for the polar angle, or pi for the polar angle and this range. And the critical thing is that this parameter lambda c, which appears in the limiting distribution, also classifies the asymmetry of the walk. And here in the Bloch sphere picture I drew the two ranges for some specific theta. Okay, now get to the final comparison between the classical random walk and the quantum random walk. So on the left, the two distributions are for the quantum random walks, and on the right we have the classical. And what we see is that the classical distribution will converge to some kind of bell curve or Gaussian, but the quantum random walk will have this nearly flat distributions which are peaked on the outside for symmetric ones, and for asymmetric ones we have either this bowl shape or some twisted version of it. What you also have to be aware of is that here the distributions can be normalized because the variance scales with n, But here the distributions really smear out because the variance scales with the square root. As a kind of bonus, we can also analytically give you the coefficients for the random walk after a specific time. And so we expand the state at some time in the number basis of the lattice and the up and the down state. And so we have those coefficients alpha j and beta j that depend on time. Sum over some combinatorial terms together with something that is depending on the unitary, and alpha and beta are the initial state. Also for classical random walks we can do the same analysis doing Fourier transform, and we get a little bit of a shorter expression which give you the probability distribution at any time. Okay, what did we do in this video? We introduced the classification of quantum random walks to you and compared them to correlated classical random walks. That's also the motivation why to investigate those quantum random walks, and we gave a closed form expression for both versions.